Hi, today we're going to talk about some ways we can improve our data quality. To do this, we're going to think a little more deeply about some of the topics we touched on in our first week, and we're also going to delve into some new topics. Now, I'm dividing the ideas we're going to cover into three categories: staying within the dynamic range of our instrument, preventing and/or identifying contamination, and verifying that our method is operating the way it's supposed to. So first, let's talk about what the dynamic range of an instrument is and how we can make sure that we're staying within it as we do our analysis. In our first week, we talked briefly about method detection limits, or MDL. Sometimes a method detection limit is based entirely on instrumental concerns, but other times it's affected by how samples are collected and processed, or factors of that nature. As a quick review, we talked about the detection limit of a method as being equal to the standard deviation of a baseline reading. But what do you use for your baseline reading? For a particular analyte, we're generally not looking at the entire spectrum. We're really just looking at one peak like here. So often we're going to be looking at just one portion of the spectrum. In these examples, we see that our analyte shows up about 7 minutes into our run. So we're going to measure the signal and noise there. Now, one way we could measure this is to run several solvent blanks, or else solvent blanks spiked with a small amount of analyte. What's a small amount? Some amount under, let's say, 5 times the MDL. Now, obviously, if you have no clue what the MDL is, this might end up being an iterative process. Eventually, you'll get some data that will help you quantify the method detection limit. For example, the EPA's method TO15, which is used to measure volatile organic compounds by GCMS, recommends running 7 blanks spiked with a small amount of analyte. And then, according to this method, the MDL would be 3.14 times the standard deviations of those blanks. That's not because it's pi, that's because it's the t-value for 7 blanks. Now, a method like this allows you to find the minimum level at which you can safely say that a reading is not noise. In other words, any reading above this MDL definitely shows the presence of your analyte. But even if you get a reading above your MDL, you can't be sure that the instrument is accurately quantifying it. For example, let's say that when determining the MDL for method TO15, the standard deviation of your spiked solvent blanks was 1.15 parts per million. That would make the MDL for your method about 3.6 parts per million. Now let's look at this reading here, which represents a concentration of 3.87 parts per million, which is definitely above the MDL. So that tells us we definitely have some analyte present. But do you know exactly how much analyte you have? You're close enough to the MDL that some part of that 3.87 parts per million signal is probably noise. How much? Who knows? So oftentimes we'll also talk about a limit of quantitation, or LOQ, which is the lowest concentration at which we feel comfortable assigning an actual number to a reading. In general, the LOQ is going to be derived from the same experiment that we used for the MDL, but we're going to multiply our standard deviation by 10. In this case, that would give us a value of 11.5 parts per million for our LOQ. Basically, if we get a reading between our MDL of 3.6 parts per million and our LOQ of 11.5 parts per million, that means we definitely have analyte in our sample. We just can't be sure quite how much. For an analytical chemist, it's rarely good enough to say that an analyte is present. We want to know how our analyte concentration compares to some sort of guideline. For example, the EPA limit for lead in drinking water is 15 parts per billion. So saying that there's definitely lead in your drinking water isn't good enough. Is the amount of lead greater than or less than 15 parts per billion? So generally, we set the LOQ as the lower range for what we want to read from any instrument. So what would be the upper limit for our working range? Again, we go back to a concept that we talked about in week 1, the limit of linearity. Remember, the limit of linearity is the point at which your method can no longer take in additional signal from your analyte, about here on this graph. As long as your analyte concentration falls between these 2 points, which is what we call the dynamic range, the readings you get for your analyte should be accurate and reproducible. Big emphasis on should. So what happens if your concentration falls outside of this range? Well, kind of depends what method of analysis you're using. If your reading's too low, for some methods, you can inject twice as much samples, so there's more analyte for your instrument to read. In UV-vis spectroscopy, you can use a cuvette with a longer path length. But sometimes there just is no way to measure that amount of analyte. And, in some papers you read, you might see a notation that says something like BDL, which stands for below detection limit, which means they might think they detected something, but they're not sure. So if your reading's above the dynamic range, a lot of times you're just going to dilute your sample in a very precise and quantitative fashion, i.e. pipettes and volumetric flasks. You don't always know how much you need to dilute your sample, so this may be an iterative process. Remember, the way you're probably going to find out that your concentration is too high is actually to run a sample and find that the concentration you get is over the limit of linearity. Let's say that the limit of linearity for your instrument is 100,000 counts, and the reading that you got on your original sample was 150,000 counts. You might think that your sample is 50% higher than the limit of linearity, so maybe you try diluting it by a factor of 2. But remember that above the limit of linearity, the concentration does not go up in a linear fashion, so the actual concentration may be 3 times the limit of linearity. So if possible, it's good to look at historical records for your source, not because they indicate the actual level that's there now, but because they're going to give you at least an order of magnitude that's reasonable to expect for your concentration. That will help you figure out a dilution factor. So next up, we're going to talk about how to deal with contamination. Now, obviously, we want to avoid contamination if at all possible, but it may not be 100% avoidable. So we want to know, is there contamination? If there is, how much is there? Knowing where it came from also helps us understand how to reduce contamination in the future. So let's start with the easy part, which is trying to avoid contamination in the first place. How you do this is going to be very dependent on what your analyte is. But a very important thing to do is to choose appropriate tools to work with and make sure they are cleaned appropriately. For example, if you're looking at very small concentrations of metals, you don't want to use any metal implements when processing your sample because those implements could put small amounts of metal contamination into your sample. When you're looking for organic chemicals, you don't want to use a lot of plastic stuff because plastics are made of organic chemicals. You're also going to want to ensure that all of your tools and containers are free from contamination. Not only contamination of your analyte, but anything else that could serve as an interference in your method. When doing metal analysis, the best way to clean glassware, bottles, or other tools is to acid wash them. Now, metals are very likely to stay in solution in highly acidic environments, which keeps them from adhering to surfaces. But just acid washing is not enough. The biggest source of metal contamination in the lab is actually dust blowing out from the HVAC system. So we never air dry bottles that have been acid washed. These are always stored in a plastic bag or other container to protect them from dust. Now, by contrast, if you're dealing with organic analysis, a lot of times you're going to rinse your glassware and other tools with some sort of organic solvent like isopropanol, and then bake them in an oven to evaporate any remaining organics. Again, you're going to want to protect your glassware from any outside contamination after you clean them, because some of this stuff is floating around in your lab. Now let's say that there did seem to be some contamination despite your best efforts. How could you tell? And how could you figure out how much contamination there was? The first thing you can do is to create a special set of blanks designed to find contamination. You're probably already going to be running a solvent or matrix blank through your instrument, but there are other sorts of blanks that you could run. First of all, you can run a lab blank. Once again, as with a normal blank, this starts with your solvent or matrix. But instead of just putting it directly into your instrument, you're going to run it through all the procedures that your sample undergoes. So for example, if you're going to analyze some stream water for metals using the ICP-MS, normally that's accompanied with filtering it. And that step might add contamination. So in this case, the purpose of your lab blank is to test whether the filtering process introduces contamination into your sample. So you would filter it and then prepare it as you would any other ICP sample that you picked up from a stream or whatever. The second sort of blank you can run is a field blank, which is used if you're collecting samples outside of the lab environment. Once again, this is going to start with your solvent or matrix. And once again, let's say you're collecting some stream water. Now, as you saw in our sample collection video, you'd start by doing a triple field rinse of the empty container before filling it with your sample. But during that time that it's got the lid off, it's open to the environment. And let's say it's a windy day. There might be small dust particles that end up in your sample that aren't part of the stream water. So what you'll do in this case is take an empty sample container before you leave the lab and triple rinse it with DI, and then fill it with DI and put the cap on. You're going to take it out to the sample site, open the lid, and leave it open about as long as you would leave a regular sample container during the sampling procedure. So if you do get a windy day or something like that, you can quantify exactly how much metal contamination you got from blowing dust. Now you're confident that you know whether your sample is contaminated or not. You get to think about how to verify that you have a nice solid method. And I could mean many things when I say that. You could have developed a new method and you might want to show everyone whether or not it works and how well it works. Or you might not trust how well you know how to use an existing method. For example, when I have students make a calibration curve for UV-Vis and ask them to write a discussion section with error analysis, one of the most common statements I see is, "Oh, maybe I don't know how to pipette very well." This is one reason we do a quality control check, often abbreviated as QC. Your QC check helps you figure out if something about your external standards has gone wrong. And there are a whole bunch of things I could be referring to with that statement. Maybe you really don't know how to pipette, or maybe the stock that you made your standards from has gone bad. So what you're going to do is make a quality control solution with a concentration that falls somewhere in the middle of your calibration curve. When you make the QC, you're going to use a different chemical source than you used for your external standards. Now, different instruments have different QC requirements, but in general, you're going to want to get the QC within 10 or 20% of the concentration you think it should be. So if you think you made a 50 parts per billion QC, but according to your calibration curve, it's 80 parts per billion, something is definitely wrong. I referred to internal standards in our first week video. At the time, I spent a lot of time talking about how to use internal standards that were basically known amounts of analyte added to your sample. But I also mentioned that sometimes we use internal standards that aren't the same as your analyte. And the reason we do this is to make sure our instrument is responding properly. For example, if your instrument normally reads 100,000 counts for a known amount of internal standard, but today it's only reading 50,000 counts, you might need to do some maintenance on your instrument. Now, when you're picking an internal standard, you want to make sure it has similar characteristics to your analyte. Well, at least as far as the instrument is concerned. For example, when you run water samples on the ICP-MS, your analytes are detected by their mass, so you want to pick an internal standard that has a fairly similar mass to your analyte. However, you always want to make sure that whatever internal standard you pick is not likely to be found in your sample, and for the ICP-MS, we use really rare metals. Another thing we often test when doing method verification is a recovery percentage. The whole idea behind this sort of test is to figure out if you're losing analyte during your sample processing. So what you're going to do is spike a solvent or matrix blank with a known amount of analyte, and you're going to run that through all of your processing steps and then analyze it just the way you would a sample. So if you originally added 100 parts per billion of your analyte, but you only measured 50 parts per billion after your test, chances are pretty good that 50% of your analyte is getting lost in processing, which is a clue that you need to fix your method. Now, just because you get a bad recovery percentage doesn't mean your method is horribly flawed. For example, we've personally found that for some analytes, you have to be very careful which filters you use. Another test that you can run for method verification is what we call a surrogate. We tend to only use surrogates if a method is very new or if you were getting a very bad recovery percentage. Basically, what you're going to do is find a chemical that's very similar to your analyte in a way that your instrument will detect. Once again, you're going to run the surrogate through all of the sample processing steps and see if it is detected by your analytical instrument. And again, you're going to do a recovery calculation on the surrogate. Now, if you get a low recovery percentage, either for your analyte or for your surrogate, that could tell you that there's some sort of interference in your sample that's interfering with the method. Now, I wish there were an easy way to identify what interferences might exist, but it's often just trial and error, frustration, lots of time on the job, etc. Your goal here is not just to identify the interferences, but also figure out a way to get the interferences out of your sample by removing them completely, or finding something that will bind to them to keep them from being analyzed. Or if you can't do that, then at least find a way to quantify the interferences independently from your analyte, so you can then mathematically adjust your concentrations that you measure. So this has been an extremely brief overview of how we check our data quality and verify our methods. And I have to say, it's very hard to teach this sort of thing in the classroom. Almost everyone I know has really gotten to understand these concepts in the lab or on the job. But at least if you understand the basic ideas, you can know that there are solutions to bad data. Your response to bad data should not just be to swear, although I admit I've done that when things got really bad, but to get out a playbook and try to figure out how you can improve your data and figure out where your issues are. And then once you've done that, you can address those issues. So I hope this was helpful, and I look forward to seeing you again soon.